So we're going to finish up relativity, the dynamics of relativity or energy in relativity, and move on to waves pretty soon. But there's just a couple more things that I want to do. One, let's just go ahead and review where we are with relativity and energy. We had the kinetic energy, the relativistic kinetic energy was gamma minus 1 times mc squared. And we had the total energy of gamma mc squared, leaving us with a rest energy of mc squared. Okay, so, and then you have to understand what this means. This means that this is, now we're not talking about potential energy here. We're talking about the total intrinsic energy in a body. A body has a certain amount of energy due to the fact that it's got mass and due to the fact that it's got motion. So we're not talking about potential energy here. But we are talking about the total energy of a body, right? So that independent of other masses around it which give it potential energy. Remember, what potential energy is when we talk about gravitational potential energy, it's due to the fact that the body in question, let's say it's a baseball, is in the vicinity of the Earth. But the baseball itself has a total energy due to its being a baseball. And that total energy of the baseball that's independent of its relation to the Earth is gamma mc squared, or the total rest energy of the baseball is mc squared. And what do I mean? What am I getting at? Is that there's if you take the baseball and you heat it up, you know that baseball has more energy in it, right? If you heat it up, it's got more energy in it. And what Einstein said is that energy, it has a mass equivalent. In other words, if you heat it up, basically the baseball is more massive. It's not going to be noticeably more massive in this case of taking a baseball and just heating it up on top of a stove, but it's going to be more massive. Or, for example, if you've got a car which has a certain amount of kinetic energy, right? And that car comes to a stop, and it doesn't. All right, the car comes to a stop, k equals 0, and the car doesn't dissipate any energy to the atmosphere around it. So in isolation, if it doesn't dissipate any energy to the to the atmosphere around it, then the mass of the car must be heavier. It must be greater. So this might sound a little strange, but really where it becomes noticeable and makes a little bit more sense is, let's take two subatomic particles in an accelerator. When we take those two subatomic particles in an accelerator, and what we typically do is we accelerate them to very high speeds, and so this might have a kinetic energy of k1, and this might have a kinetic energy of k2. And I'm sorry, kinetic energy is not a vector. Oh my gosh, be careful, it's not a vector. I'm just indicating that it's got a velocity in that direction, giving it a kinetic energy. So if those two particles collide, right, these are subatomic particles in a particle accelerator, if those two particles collide, what happens? You probably know that in an accelerator, when you collide two particles, because you often are looking for what comes out of that collision, it's not just two billiard balls that are going to bounce off of each other. And what happens is you sometimes get out different kinds of particles, and you get out energy. Right, so it's this concept that the kinetic energy, if those two particles collide, you're going to get out of that collision, you're going to get some kinds of photons, right, which is just pure energy, and you might get out some different kinds of particles. So let's say this is particle 1 and this is particle 2, and then this is some unknown particle that you get out. So, but that unknown particle might have a different mass than 1 and 2. Where'd the rest of the mass go? The rest of the mass went into energy that went out as light, or as photons. And we indicate photons. I think we've talked about this before, but if we haven't, photons are indicated as gamma. That's not the same gamma as the Lorentz factor. That just indicates photons, right? The fact that it's a photon. So don't get confused there. But anyway, so you have some kind of collision between two particles in an accelerator, and what you get out are all kinds of energy and other particles. And when you add up all the energy, right? So you add up the mass, the kinetic energy, and the energy in the photons, it must equal the total kinetic energy, the total, the total energy of each of the first two particles. So that means that gamma m1 c squared, gamma 1, sorry. Okay, I gotta be careful here. Oof, this is getting complicated. Let's get rid of gamma for the photon, just so we don't get confused. That's just photon 1 and photon 2. It just indicates that energy is being released, right? Electromagnetic energy, photon 1 and photon 2. Electromagnetic energy is being released. Okay, so you've got, so the gamma here now is the Lorentz factor. So you've got gamma m1c1 plus gamma m2c2 squared is the total energy in this collision. Total energy in the collision. Out of the collision, we get a whole bunch of new particles, right? So we've got gamma of the new particle. We can measure the speed of the new particle times the mass of the new particle times c squared plus some electromagnetic energy, right? Some, what do we want to call that? Energy of photon 1 plus energy of photon 2. They're not particles, right? Photons are not particles. They don't have mass. Make sure you understand that photons do not have mass. They just have energy. So that equals the total energy. And so this is the energy in, this is the energy out. So energy in equals energy out. Still, energy is conserved. So what we're showing here is that what was kinetic energy and mass energy, has turned into some kinetic energy and mass energy and additional electromagnetic energy, right? All energy is the same. And that's what I meant with the car coming to a stop, right? That the car had kinetic energy, it had mass energy, and when it came to a stop, as long as it didn't dissipate energy to something else, then all of that energy still had to be there somewhere. So since the kinetic energy went away, where'd it go? It went into the mass energy of the car increasing. So the mass of the car actually increases. That is not actually strange, and it doesn't seem strange. I mean, it should seem strange, but it's not actually strange, and it won't seem strange when you're talking about, a subatomic collision. It's just you don't think of that kind of things with masses, with cars. So we can turn mass into energy and energy into mass. And again, that's not always easy to do. Like we said last time, if you want to turn Nick into energy, you've got to find an anti-Nick, Nick's antiparticles in order to combine him with, in order to annihilate him and turn him completely into energy. But anyway, this is the energy as it's understood by Einstein's relativity, and it is correct, and it's been shown to be correct. So now, one more thing I want to point out, and that's going back to our energies and remembering that momentum, I'll just leave it as red. Momentum is gamma mu. For a particle, we can relate the energy of the particle, the total energy of the particle, to the total momentum of the particle. Just like classically, if k equals 1/2 mv squared and p is equal to mv, therefore you can see that k is equal to p squared over 2m. So I just want to relate the total energy to the momentum. And you can do that, and it's just algebraic manipulation, just like we did here. So I'm not going to do it out, and I'm just going to write the result. The result is that the total energy squared, which is gamma m0 c squared squared, you can show, I would say, and maybe I'll even assign it for homework, but you can show that that is equal to m squared c to the fourth plus p squared c squared. That's important. This is an important relationship because what Einstein was able to further show is that if you have a massless particle, such as a photon, and there are other massless particles, if you have a massless particle, therefore m0 is equal to 0, and therefore E squared is equal to P squared C squared. So therefore E is equal to PC. So the energy of a massless particle is equal to the momentum of a massless particle times the speed of light. Now, what does this tell us? You might just say, oh, that was an algebraic manipulation, but there is something fantastic that comes out of this, right? E equals PC for a massless particle. What does this tell us? I'm going to tell you because you could just pause and think about it. What's strange about this? What's strange about this is that a massless particle has momentum. That massless particles have momentum. And Einstein was able to show that massless particles have momentum, that light has momentum. And that is absolutely 100% true. It can be shown, it can be proven, it can be experimentally shown that even though they don't have mass, they have momentum due to the fact that they have energy. This fact, E equals PC for massless particles, is an important fact that will come up in our future chapters when we're talking about the justification of quantum mechanics. This is going to come up again. So this is an important point that we need to remember for later.